Okay, ma'am. So next topic. Next topic discussion on okay, ma'am. See, next topic discussion on cyclic photophosphorylation. The electrons released by P700 of PS1. PS1, so it absorbs 700 nanometers light from the environment, so and releases electrons. In the presence of light, those electrons taken up by the primary acceptor and then passed on to ferredoxin, plastoquinone, cytochrome complex, plastosphene, and finally back to P700. That is, electrons come back to the same molecule after cyclic movement. See, here before that I said cyclic phosphorylation. So in that cyclic phosphorylation, sorry, non-cyclic phosphorylation, okay. So non-cyclic phosphorylation. So in the non-cyclic phosphorylation 2, PS1 and PS2. First PS1 2 is involved. Next PS1 is involved. Okay, but in cyclic phosphorylation, only PS1 is involved. See, PS1. It absorbs P700 nanometers light from the sun rays. So it transfers electron to the primary electron acceptor, primary electron acceptor. Primary electron acceptor already non-cyclic photophosphorylation. I said that. That is what quinone. So these electrons from the quinone, this is called primary electron acceptors. So from the quinone, these are transferred to the plastoquinone, plastoquinone to cytochrome complex. That means what? Cytochrome B, cytochrome F, cytochrome B6, like that. Next one is plastocyanin. So plastocyanin 2, those electrons again come back to its original position. This is called cyclic photophosphorylation. So before that, what we have discussed, so from PS2, the electrons are transferred to the electron acceptors. From the electron acceptors, these are transferred to the PS1 and then to the FRS and then to the NADP. Okay, here water splitting and releases protons. Among those protons, some protons are added to the NADP, it becomes NADPH2. So it is a cyclic phosphorylation. It is non-cyclic phosphorylation, like this way it will go. So in this one, it is also called light reaction. Light reaction is also called non-cyclic phosphorylation. So in non-cyclic phosphorylation, PS2, PS1 is involved. But electrons are not reached to original place, first place. But in this one, so the electrons are transferred from PS1 to electron acceptor. And again, those are reached back to the PS1. This process, electrons are released, and again those are come back to its original position. That's why this process is called cyclic phosphorylation. It is also called cyclic phosphorylation because it occurs in presence of light. Okay, ma? So this is called cyclic phosphorylation. Okay, ma? So whatever I said, that is here will be there. See here. So from the these are all electron acceptors: ferredoxin, plastoquinone, cytochrome complex means what? Cytochrome B6, cytochrome F, so plastocyanin, and finally back to P700. So PS1, it's 700 700 nanometers wavelength. That is, electrons come back to the same molecule after cyclic movement. The cyclic photophosphorylation is also result in the formation of ATP molecule, just like in non-cyclic photophosphorylation. In non-cyclic photophosphorylation, how ATP released? In the same way, even in cyclic photophosphorylation also, ATP is released. So as the electrons move downhill in the electron transport chain, they lose potential energy and ATP molecules are formed in the same way as in mitochondria during transpiration. See here, electrons, see here, the electrons are moving downward movement. So what I said, PS1. So PS1, from the PS1, electrons transferred to the primary electron acceptor. From the primary electron acceptor through some other electron acceptor, through electron acceptor molecules, those electrons comes here, and again those are come back to original position. So while moving these electrons downward movement, it is goes upward and again downward movement in the mitochondria and chloroplast. So and again come back to its original position. That's why when molecules are moving from upward to downward, in non-cyclic photophosphorylation, what from higher concentration to lower concentration, while moving protons, a kind of energy is released, ATP. In the same way, like that only in this one only, when the electrons are moving from upward direction to downward direction, here a kind of energy is released that is called ATP. This process is called cyclic photophosphorylation. Cyclic photophosphorylation. Okay, ma, that's all. So this is cyclic phosphorylation. So light reaction, in the light reaction flow chart, whatever I said, that is only non-cyclic photophosphorylation. But in cyclic photophosphorylation, only PS1 is involved. Important facts here. So when the two photosystems work in series, first PS2 and then PS1, a process is called non-cyclic photophosphorylation. PS2, electron acceptor molecule. Then PS1 from FRS. From FRS to here one more molecule, ferredoxin. From the ferredoxin, these are to NADP. So here water splits molecules are added, then it becomes to NADPH2. Okay, this process is called, seems to be a Z letter. This is called Z scheme of reaction. It is also called non-cyclic photophosphorylation. See, the two photosystems are connected through a electron transport chain as seen in the form of Z scheme. See ma, here two photosystems are connected through the electron transport chain. See, photosystem 2. This is called electron acceptor molecule, that is quinone, plastoquinone, cytochrome F, cytochrome B, like this way, plastocyanin. So through these electron acceptors, these are all called electron acceptor molecules. So the electrons are reached to the PS1. So through these electron acceptor molecules, electrons are transferred. Therefore, it is also called electron transport chain. So from the PS2, these are transferred to the electron acceptor molecule. From the electron acceptor molecule, through a series of electron acceptor molecules, it is reached to PS1. From the PS1, these are again goes to the FRS, ferrous reducing substance. It is called ferrous reducing substance. From this ferredoxin. Okay, from the ferredoxin, these electrons transfer to the NADP. Okay, here water molecules are split. At that time, 4 protons are released. So those protons are transferred to the NADP, and then it becomes to NADPH2. Okay, so in this one, the electrons are transferred through the electron acceptor molecules. Therefore, it is called electron transport chain. electron transport chain. Okay, so the electron transport chain, it seems to be jet scheme. Already I said it, the letter seems to be jet scheme. That's why it is PS2, here PS1, here FRS, here electron acceptor molecules. It seems to be jet scheme. Only when only PS1 is functional, electron is circulated within the photosystem, and the photophosphorylation is due to cyclic flow of electrons. Okay, in cyclic photophosphorylation, electrons were released and again reached to that place. So that is called cyclic flow of electrons. It occurs in stroma lamella. So stroma lamella, it is chloroplast. Stroma, this region is called stroma. In this stroma region, cyclic phosphorylation takes place. Okay, so the stroma lamella lacks PS2 as well as NADP reductase enzyme. See here one point I wanted to say here. So NADP reductase enzyme. So see here, so 4 protons are added to the NADP. This was initiated, catalyzed by the NADP reductase enzyme. So NADP becomes NADPH2 with the help of enzyme. That enzyme is called NADP reductase enzyme. This reductase enzyme catalyzes this process and makes the formation of NADPH2. Okay, ma? That's all. Next here, that only. NADP reductase enzyme. The excited electrons does not pass on to NADPN, but is cycled back to PS1. That only. So the excited electrons does not transfer to the NADP because NADP ion was not there. In cyclic photophosphorylation, NADP ion was not there. That's why it is not added to the NADPN. So cycled back to PS1. The grana lamella have. So both PS1 and PS2. Grana lamella means what? See here, grana lamella. This is chloroplast. So this is grana. So this is called grana. So in this grana, PS1 and PS2 are present. But why PS1 and PS2 formed here? Chlorophyll A responsible for the formation of PS1 and PS2. But in stroma, so this is called stroma. This is called stroma. This is called stroma. In this stroma, only PS1 is present. PS1 is absent. Okay, ma? That's all. So the grana lamella have both PS1 and PS2. But stroma has PS1. Okay, ma? That's all. See differences between cyclic and non-cyclic phosphorylation. Actually, this topic in textbook they did not give like differences, but separately given. Separately given. So in exams they will ask this question. That's why I am taking this one. So non-electron, non-cyclic, cyclic. If you study that is perfectly, that is what here you will write. How you will write? Electrons don't come back to the same molecules. In non-cyclic photophosphorylation, electrons don't come back to the same molecule. See, electrons are from here. So from the water splitting of water molecule, electrons are joined to the PS1. So these electrons are pushed to electron acceptor by photons, which are received from the sunlight. So these electrons are goes and forms NADP, but does not come back to its original position. Okay, ma? So that's all. That's why it is called non-cyclic. But cyclic, those electrons come back to the same PS1 goes to the electron acceptor molecules and reach it through the electron acceptors and again come back to its PS1. That's why it is called cyclic phosphorylation. First electron donor is water. In non-cyclic photophosphorylation, electron donor is water molecule. Already I said electron donor. So for this non-cyclic photophosphorylation, electron donor is splitting of water molecule. This water molecule splits and releases 4 electrons. Oxygen is escaped into the atmosphere. Protons. That's all. So here electron, first electron donor in photophosphorylation is PS1. Okay. So from the environment, from the sun rays, it will take electrons. PS1. So first electron donor is PS1. PS1 means what? 700. It absorbs 700 nanometers. From this 700 nanometers, it will absorb electrons. Those electrons are transferred to the electron acceptor molecule. involves both PS1 and PS2. In non-cyclic photophosphorylation, both PS1 and PS1 involves. In this one, PS1 only involves. The last electron acceptor is NADP. Last electron acceptor, final electron acceptor is NADP. So NADP is electrons accepted. That's why NADP is also called reduced NADP. So when the word reduced we have to mention NADP H2. That means 2 protons are accepted. Here last electron acceptor again P700. See, so electron acceptor through electron acceptor molecules, electrons again come back to PS1. So the net products are non-cyclic photophosphorylation, nothing but light reaction. I think so. No need to do specific flow chart for light reaction. I said so for specific light reaction flow chart. I will make it and do. I will make a video and I will share. I said, but specifically now it is no need. So non-cyclic photophosphorylation, nothing but light reaction. About this many times today only. Many times I have drawn that flow chart. So the net product are ATP. The end products of light reaction are ATP. The end products of non-cyclic phosphorylation ATP, NADPH2 and O2. See, this is only flow chart for light reaction. Okay, even though I will make it, no problem. Okay, that's all. So here last electron, the net product is ATP. In this one, non-cyclic photophosphorylation, the only ATP is formed. Why not other formed means here water molecule is not involved and the NADP is not involved. NADP ion is not there. So that enzyme also not there. That's why remaining products are not formed. That's all. So next topic. Differences between photosystem 1 and photosystem 2. So photosystem 1 and photosystem 2 differences. So photosystem 1 is located in the non-appressed part of grana thylakoid. Non-appressed means what? Not a specific part of grana. PS1 is located in the non-appressed part of the grana thylakoid as well as stroma thylakoid. Okay, so in grana, specific parts of the grana and stroma lamella, PS1 is not there. So PS2, the PS2 is present in the appressed specific parts of the grana thylakoid. In the grana thylakoid, specific parts of the grana thylakoid, it is present. Specific parts of the grana thylakoid, it is present. Okay, that's all. Next, chlorophyll A content is more than twice that of the chlorophyll B. In PS1, chlorophyll A content is more than that of the chlorophyll B. So in PS2, chlorophyll A and chlorophyll B are approximately equal. So has reaction center P700. So photosystem 1 has reaction center P700 nanometers reaction center. It has P680 nanometers reaction center. So receives electrons from the photosystem 2. So PS1 receives electrons from the PS2. Electrons are received from photolysis of water. PS2 receives electrons. See here, see photosystem 2. This is photosystem 2 receives electrons from the splitting of water. So photosystem 2. So photosystem 1 receives electrons from the photosystem 2. Okay, that's all. That's all. So receives electrons are received from the photolysis of water. PS2 receives electrons from the photolysis. Can perform cyclic phosphorylation independently. So photosystem performs cyclic photophosphorylation independently without taking any other factors support. Here performs nanocyclic photophosphorylation in conjunction with photosystem 1. With the help of photosystem 1, so it can be performed cyclic, non-cyclic photophosphorylation. So not connected with photolysis of water. So photosystem 1 not connected with photolysis of water. So connected with photolysis of water, usually hands over electrons to NADP. So in photosystem 1, so usually hands over to its electrons to NADP ion. Usually hands over its electron to photosystem. See here. So photosystem 1 usually hands over its electrons to NADP ion. So usually here hands electrons to photosystem. That's all. Okay. So whatever may be the electron photosystem 2. So receives electrons and transfer to the photosystem 1. Photosystem 2 receives electrons and transfer to the photosystem 1. From the photosystem 1, it goes to FRS to ferredoxin to NADP ion. NADP ion. That NADP, so NADP ion receives electrons from the PS1. See here. So NADP ion, actually it is NADP ion before adding H2. So NADP ion receives electrons from the ferredoxin. Ferredoxin receives electrons from the FRS. FRS receives electrons from the PS1. So PS1 adds electrons to the NADP ion through electron acceptor molecules. So this is the differences between photosystem 1 and photosystem 2. Okay, so these are not given in textbook specifically, but these are important. That's why I have given. Okay, so next, electron transport chain. It is also we discussed already. We discussed. What we have discussed. See here. So the electron chain is a light-driven reaction. Light-dependent reactions of photosynthesis. Those are all called electron transport chain. It was first given by Robert Hill in 1939. So while saying yesterday light reaction, I said that light reaction is also called Hill reaction because it was introduced by Robert Hill in 1939. So light reaction, nothing but electron transport. Why electron transport? So today only I said that PS2. So PS2 receives electrons from the splitting of water and transfer them to the quinone. From them through electron acceptor, it is transferred to the PS1. Here there are some electron acceptor molecules are there already many times I said. So through them PS1 is received. From the PS1, those electrons are reached to the FRS complex. FRS stands for ferredoxin reducing substance. From the FRS ferredoxin. From the ferredoxin, NADP. From the NADP, it becomes to NADPH2 because here protons are there. Those protons are absorbed by the NADP ion with the help of NADP reductase enzyme. So through these electron acceptors, electrons are transferred to next level. So this method is called electron transport chain. Electron transport chain. Okay, that's all. So that only, it is not any fresh new topic. In an electron transport, when a molecule gains an electron, it is said to be reduced, and when a molecule loses an electron, it is said to be oxidized. See here already it was there. See, PS1 when gains electrons, it is reduced, then leaves electrons, then it is oxidized. Next, electron acceptor molecule. First electron acceptor molecule is quinone. It is first reduced, next oxidized. So here one complex. When it gains electrons, reduced, leaves electrons, oxidized, reduced, oxidized. When gains electrons, reduced, leaves electrons, oxidized. Like this way. So these are all called electron acceptor molecules. Through these electron acceptor molecules, electrons are passing. Therefore, this chain is also called electron transport chain. Already I said it. Electron acceptor chain. Okay, ma? Electron acceptor chain. Okay, ma? That's all. This is the explanation. Electron acceptor chain. Okay, see, in electron C, said to be reduced, loss an electron is oxidized. Like that, every molecule is reduced or oxidized. In electron transport chain, electrons move from one electron carrier to the next, involving reduction and oxidation reactions. Therefore, those are called redox reactions. In electron transport chain, it is initiated by absorbance of light by photosystem 2, that is P680. See, photosystem 2 receives electrons from water, and these electrons transfer to electron acceptor molecules. For the transfer of electrons, it will get energy. That energy is obtained by sunlight. That is called photons. As I said that, photons. Okay, so the PS2 receives light, photosystem 680 nanometers light. the excited p680 molecules emits an electron and it moves to the primary electron acceptor. Primary electron acceptor. Primary electron acceptor, what? Quinone. Quinone. Primary electron acceptor, quinone. So as each electron escapes from the p680, another electron must take its place. Okay. So from ps2, one electron escape to another electron acceptor molecule. Then ps2 is ready to take one more electrons from the water. It is a continuous process. Okay. So one electron when leaves, then automatically it is ready to accept another electron. Okay, that's that. So this process is the cyclic process. Like this way, like this way, like this way, continuously, like this way, continuously happens. Like a jet stream continuously happens. So that it is called electron transport chain. Electron transport chain. Electron transport chain. Okay, ma? That's it. Next, the replacement electrons come from the splitting of water molecules called photolysis. So replacement electrons, one electron, so 2H2O splits, this side 4 protons, this side oxygen, sorry, upside oxygen, this side electrons. These electrons are absorbed by the PS2. After that, and one more water molecule is ready to donate electrons. After this, and one more water molecule is ready to donate. This phenomenon is called photolysis. So the photolysis depends upon manganese, calcium, chloride ions play an important role in photolysis of water. Already on 12th chapter, while I am teaching the topic, I said, so during photolysis, manganese, calcium, chloride ions plays a important role in the photolysis of water, I said. Okay, ma? That's all. So by the photolysis of water, electrons are generated or passed to oxidized P7 PS P photosystem 680. P stands for photosystem. C photosystem 680. It is photosystem 2. So here water molecules are split and electrons are released, protons are released, oxygen is escaped into the atmosphere. So that's it. By the photolysis of water, the electrons are generated, are passed to the oxidized 680 and a molecule of oxygen is released In meanwhile, the escaped electrons passes to the primary electron acceptor. Same point many times I said. This is reduced acceptor now donates electrons to the plastoquinone and that further donates to the downstream components, that is components of the electron transport chain. Here I said here, so again I am showing. See, from the PS2 electrons are downward movement through electron acceptor. These are all electron acceptor molecules and downward and reached to the photosystem. Photosystem 1 is accept those electron transfer to the FRS, ferrous reducing substance. Okay, na? That's all. Okay, so yes, these reduced are now donates electrons and then further donates to the downstream components of the electron transport chain, that is cytochrome B3, cytochrome F, plastocyanin, and finally to the P700, that is photosystem. So like photosystem 2, photosystem 1 also emits electrons which are captured by the primary electron acceptor. This reduced electron acceptor transfers electrons to ferredoxin to reduce NADP. Ferredoxin means ferrous reducing substance to NADP. NADP becomes NADPH2. Photosystem 1 in turn draws its electron from PS2. So when electrons goes to NADPAN, photosystem is ready to take next level of. When it is transfers electron, again photosystem 1 is ready. This entire process occurs in the chloroplast, grana of thylakoids, grana of chloroplast, thylakoid of chloroplast. Okay, so this entire phenomenon is called electron transport chain. Okay, in textbook they did not maintain proper sequence. Okay, so according to the textbook, one topic here, one explanation I should give here. Here, what they have given, see, chemiosmotic hypothesis. Chemiosmotic 11.6.3. Chemiosmotic hypothesis. Chemiosmotic hypothesis, it is a part of light reaction only. In that, whatever the points were there, the same chemiosmotic hypothesis means what? In that, how protons are moving, how proton in light reactions, last two steps, NADP step, ATP step only, chemiosmotic hypothesis. So that if you study, it is also covers. Next, one more heading, where are the ATP and NADPH used? ATP and NADP were used for dark reaction, for carbon dioxide fixation. Those ATP and NADP are used. That is also in this heading. That is also morning only we discussed. So next topic, primary acceptor of carbon dioxide. That only dark reaction we discussed already. Okay. So the next final topic is the C4 pathway or Hatch-Slack pathway.